Ever wondered how AI systems like GPT-4 or DeepMind's latest models achieve human-like reasoning? Today, we're diving into the cutting-edge research that's pushing the boundaries of machine learning, exploring transformer architectures, emergent capabilities, and the ethical implications of systems that can code, debug, and even reason about abstract concepts. Let's get technical. Transformers, the backbone of modern AI, have evolved far beyond their 2017 origins. Early models like BERT and GPT-1 relied on static attention mechanisms, but recent breakthroughs in dynamic attention, such as the Sparse Attention and Long-Range Arena techniques, allow models to process sequences up to 1 million tokens. This isn't just scaling, it's redefining how models prioritize information. For instance, the recent Performer paper replaced softmax attention with a linear approximation, reducing computational complexity from O(n)(2) to O(n)log(n) without sacrificing accuracy. This is how we're training models that can analyze entire books or codebases in a single pass. Now let's talk about something fascinating: emergent capabilities. When models like GPT-3 or PaLM reach a certain scale, they develop skills not explicitly programmed. For example, they can perform multi-step reasoning, solve math problems with chain-of-thought prompts, or even generate pseudocode from natural language descriptions. These aren't just smarter versions of old models, they're exhibiting behaviors that researchers are only beginning to understand. A 2023 study showed that models with over 100 billion parameters start to demonstrate meta-learning abilities, adapting to new tasks with minimal fine-tuning. This raises a critical question: are we building tools, or are we witnessing the birth of a new form of intelligence? Let's get into the weeds with Mixture of Experts, a technique revolutionizing model efficiency. Traditional models apply all parameters to every input, but MOE splits computation. Each expert handles specific tasks, and a router decides which experts to activate. This reduces inference costs by up to 70% while maintaining performance. Take Google's GLaM model, which uses 64 experts, each specialized in tasks like translation, coding, or reasoning. The router, trained on task-specific gradients, ensures the right expert is engaged. It's a game changer for deploying models on edge devices, but it also introduces challenges. How do we ensure fairness in expert selection? What happens when a rare task falls through the cracks? But here's the catch: with power comes responsibility. Recent work on alignment, like the Direct Preference Optimization paper, aims to train models to avoid harmful outputs by learning from human preferences. Meanwhile, researchers are tackling interpretability. Tools like SHAP and GLaM help unpack how models make decisions, though transparency remains a work in progress. And let's not forget the environmental cost. Training a single large model can emit as much carbon as 500 round-trip flights. So while we marvel at these advancements, we must also ask, how do we balance innovation with sustainability? AI research is moving faster than ever, and the next breakthrough could be just a paper away. If you're curious about the math behind these models, check the links in the description for papers on sparse attention, MOE architectures, and alignment research. Hit subscribe for more deep dives into the science behind the headlines, and let me know in the comments, what AI topic should we tackle next? Thanks for watching, stay curious.